Now, before we move on to the next section, which is on nonlinearity, there is something which needs to be cleared out mm, before moving there, and that is the topic of time invariance plus the issue of linearity. So, this might be confusing at times, so I just want to clear this part, and at the end of this section I'll make a statement which I would like you to remember for the rest of this course. So what is a linear system? We have been studying this since our undergraduate days. A linear system is any system whose output can be uh, obtained as a linear sum of its inputs. So if you have an output y1t, which is a function of x1t, and there's a output y2t, and it's a function of x2t, then a system is linear if you're able to obtain a scaled output from scaled inputs. So if you supply scaled inputs to this system, the system is f, the system performs a function f. So if you supply scaled inputs in superposition, that is, you supply x1t with coefficient a, you say x1t, it's scaled, and then a sum, say, of another scaled input x2t, then when this system f operates on this scaled superposition, it should be equal to a scaled superposition of the outputs. So it should be equal to a y1t plus b y2t. That is what a linear system does. So if this happens, then we say that this system f, or this function f, is linear if it follows this principle. Now, what is a time invariant system? A time invariant system is one in which a time shift in its input results in the same time shift in its output. So if you have a function y of t, if you have output y of t for a function f, and the argument is x of t, and then if t is shifted by an amount tau, and if y shifts by the same amount tau, then this function f, or this system f, whose system response is characterized by f, is a time invariant system. Okay, so these are two separate principles, or two separate properties: linearity and time invariance. Now sometimes it might be confusing to distinguish between the two, and it might lead to some confusions. So a very typical example of that is the following system. Let's see what the system is. So we have two inputs, v in 1 and v in 2, and it's v in 1, it controls a switch, and v in 2 simply it connects to the output v out through the switch, and then there's a load resistance R1. Now we can look at this problem in two ways. We can assume that this entire thing is a black box. You can assume that this is a black box, you don't know what's inside, and then all you're supplying is a v in 1 and you're getting v out. The other way to analyze this problem is that you assume that all of this is a black box, you don't know what's inside, and you're just supplying v in 2 and looking at v out. So these are the two different scenarios in which we can observe this system, and in each scenario it behaves differently. Now this switch, before we move on, this switch, it is on if v in 1 is positive, and if v in 1 is negative, then this switch is off. Now let's see what happens in both of these cases. Okay, now let's assume that the input of interest is v in 1. That is, we are looking at how V out, if V out is f of V in 1, then what kind of a function would f be? Would f be linear? Would f be time invariant? So these are the two questions we're trying to answer. If V out is expressed as a function of V in 1, then what kind of a system do we have? Now let me clear the screen first, so we have a clear screen to start with. Yep. Okay, so the first question is it linear? Is it linear? Now what does that mean? That means if I scale the input, so if I scale V in 1, say for example 8 times, V out should also be scaled 8 times, right? That's what it means for a system to be linear. Now, for example, I have a certain, so for example, if the switch is on, right? If the switch is on, V out is equal to V in 2, as we see from the system. If the switch is on, that is if V in 1 is greater than 0, V out is V in 2. If V in 1 is less than 0, V out is equal to 0, because it's simply, in that case, it's connected to ground. In that case, the switch is open, so this is an open circuit, and all V out is seeing is ground, so there's no voltage. So this is the case. This is how the system is behaving. Now this is clearly a non-linear system, because no matter what I do to V in 1, if V in 1 is, suppose I start with a V in 1 of 3, right? Then V out is V in 2. Now suppose I double this value. Suppose I have a V in 1 of 6. V out is still V in 2, right? So V out doesn't scale with V in 1. So that makes the system non-linear. So the first part is done. The system is non-linear. Okay. Now on to the second part. Is it time invariant or is it time variant? Remember, we are treating the system as a black box. All we are interested in is how the system V out behaves with V in 1. We are looking at a relation V out is a function of V in 1, and we are trying to understand how this f, what kind of a function this f is. So now we know f is non-linear. That is one thing we know about f. The other thing which we can guess about f is whether it's invariant, time invariant, or time variant. Now how do we calculate that, or how do we understand if it's time invariant? Now what you do is you simply think of, again, you have, if V in 1 is greater than 0, then V out is V in 2. If V in 1 is less than 0, let me put T's in there. Let me put T and let me put T. Right. Now, assume this case. If V in, as a function of T, V in 1 is less than 0, V out is always 0. No matter if I apply this V in 1 with a time difference, as long as it's negative, V out will be 0, right? So what does that mean? That means that every shift in time which I apply to V in 1 does not necessarily correspond to a shift in V out. So that means the system is not time invariant, which means it's time variant. So time invariance is not there, which makes the system time variant. Okay, so the system is non-linear and it's time variant. Okay, now let's look at the other case. Now if we say that the input interest is V in 2 and not V in 1, so all of this is a black box and this is your input of interest. Now what happens to V out? Now V out is simply V in 2, right? Now again, this is if V in 1 is greater than 0 and V out is equal to 0 if V in 1 is less than 0, right? But in this case, we're not concerned with how V in 1 changes, right? For a given V in 1, if I double V in 2, right? If I double V in 2, V out will double. And in this case, it does not apply because then we're not talking about V out as a function of V in 2. In this case, V out is constant anyway. This scenario only applies to the case where V in 1 is greater than 0, because only in that case can we talk about V in 2 and V out, right? So this case does not apply, and in this case it is obviously linear, because if you scale V in 1, if you scale V in 2, V out also scales by the same magnitude. So this system, this box, this system is linear. So if I express V out as a function of V in 2, so if V out is G times V in 2, whereas earlier we saw V out F times V in 1, right? So this F was non-linear, this F was time variant. Now this G is linear, because if you scale V into V out 2, V out also scales, and again this is time variant. Now this G is also time variant, because no matter what you do, for example, if you have, let me clear the screen again. For example, if you have V out, so function of t is G times V in 2. Now this relation does not necessarily hold. That a shift in V in 2 might not necessarily mean that you'll have the same V out with a time shift. We'll see an example and we'll see why that's not the case. Let's look at this. So so this is the system. Let's assume some waveforms. So this is V in 1 and this is V in 2. So you apply a waveform, you apply a sine wave at this, you apply a sine wave at this, right? And now you look at what V out does. So for every position where V in becomes negative, right? For every position where V in becomes negative, your V out goes to 0, right? And then your for every position where it's positive, V out follows, so it follows V2, V in 2. So it completely follows V in 2. Now suppose I shift V in 2. So if I have V in 2, t minus tau. Suppose I shift this waveform, right? And this is V out. If I shift V in 2, then the shifted V out, which would be V out t minus tau, the shifted V out will not be same as you know, as this. Right now, this thing, remember, should not be confused with okay, this might be a confusion. Let me clear that first, erase everything. So this is V out, right? This is V out. Let me just draw it here. It's something like this, something like this, right? So this is V out, and V out, this is V out t minus tau would be exactly this with a time shift, right? So this would be the starting point, and this would be some time shift tau. So this is what V out t minus tau would look like. Its shape would be exactly like V out, but g times V into t minus tau is something different. What does this mean? This means that I have shifted V into, and now I'm passing it through this system. That will be a completely different waveform. So for example, it goes through the system like this, right? Let's assume it goes through the system like this, right? Let's assume this is the shifted signal and this is tau. So what will happen? All of these areas would be 0, right? And this would be the positive one. So it will be something like this. So the resultant would be something like this, right? And then it would go to 0. And then it would be like this. And then it would again go to 0. Then it would be again something like this. So this shape, if you look at this shape, it's completely different than V out, even the shifted V out. So it's a completely different shape. So from this example, it should be clear that this system is not time invariant. It is a time variant system. Okay, it's a time variant system, both with respect to V in 1 and V in 2. Okay, so it's time variant with respect to both V in 1 and V in 2, and with respect to V in 1 it is non-linear, but with respect to V in 2 it's linear. Now with respect to V in 2, there's something which we need to understand. Even though the system is linear, right? The system is linear, it can still generate harmonics. This is something which is not it's not intuitive, but this is exactly the purpose of this section. I want you to remember, I mentioned that there's something I want you to remember. The point I want you to remember is that a linear system can generate frequency components that do not exist in the input signal when the system is time invariant. Okay, a linear system. So this is important. Normally when we talk about distortions, when we talk about harmonics being generated, we talk about nonlinear systems. But even a linear system can generate harmonics as long as it is time variant. This is an important point which I want you to remember for the rest of this course. And if we look at the maths, we know that V out is V into times S of t. And what is S of t? S of t is nothing but a switching function, because V in 1. So if this is your, and this is your switch, right, and this is your R, and this is your V out. So this is nothing but a switch. So this switch will have a switching response, right? Maybe a switch train or something. Now, if you look at V out, it is nothing but V into times the switching response. Now, it might have a different shape, but it's still some sort of a two-level signal, right? It will have a 1, it will have a 0. It's a two-level signal. It will always be a square wave, right? It will always be a square wave, because that's how switching signals are. They're always square waves. So it will be a square wave, and then it's multiplied by V in 2. Now, these square waves, we can always represent them with an infinite series of impulses. This is, again, we mentioned that we will need some background from signals and systems, and this is exactly the point where we need that. So if we switch from the time domain to the frequency domain, we know that products become convolutions. So this product changes to a convolution, and then V out in terms of time becomes V out in terms of frequency. So this is the spectrum of V out. The spectrum of V out would be the spectrum of V in times the convolution, convoluted with the spectrum of a square wave signal. Now, the spectrum of a square wave signal is nothing but a sinc function, right? You should remember this from your signal systems class. So it forms sort of a sinc function, and then for example, this is your spectrum. This is the spectrum of your input signal V in 2. The output would be the convolution, and the way we do convolution is we sweep across this this frequency band through all those different frequency components. I'm sure you must have done this in your signals and systems class. You just take this function and you sort of sweep this function across this impulse response, and then you get the same function across all these different responses. So that is how your output looks like, and this is exactly how it looks like. So now we have generated harmonics, right? We have generated harmonics, remind you, from a linear system. And what's the catch? The catch is that the system should be time variant. Now, this is an important point, and I want you to remember this point for the rest of this course, that linear systems can also generate harmonics if they are time variant. And with this, I'll end this lecture on core principles. In the next lecture, we'll look at nonlinearities in RF systems.